My name is Andrew Elliott. I work at the MD Anderson Cancer Center. I work in the lab of Dr. Caroline Chung in the Department of Radiology. My talk today is entitled Probabilistic Detection of Small Tumors Using Wavelet Techniques. Okay, first of all, the motivation for this. Due to the improvement in imaging techniques, there has been noticed a relative uptick in the number of brain mets being detected. That's not necessarily because there are more brain mets, it's just because of the improvement in the imaging techniques. And it's estimated that 40% of patients with solid tumors, as many as 40%, may experience brain mets, so mets will travel to the brain. Management of these is a complex issue, and high precision imaging is one of the key factors for actually treating this condition. Sorry. Okay, so one of the challenges with small metastases, and this is one of the things we're particularly working on, and I mean metastases of a diameter less than 5 millimeters. Okay, so they're quite small, and they can actually look like blood vessels. They can look exactly the same as blood vessels. In fact, if you look at the images over here on the right, I have deliberately not labeled them, and I wanted people to guess which one was the tumor and which one was the blood vessel just by looking at them. The one down the bottom is the tumor, okay, and the one up the top is the blood vessel. And it's actually very, very difficult to distinguish them on these images. These, by the way, are contrast-enhanced 3D MRIs. And also, for these types of tumors, according to the literature, very little work, relatively speaking, has been done on tumors this size compared to larger tumors. So that's another reason for doing this. Sorry. Okay, in the details, all the data was collected from patients at MD Anderson using the institutional protocols. The cohort consisted of adults that had melanomas, lung tumors, and breast tumors, all of which had metastasized to the brain. The method of imaging was 3D contrast-enhanced MRI. And the tumors themselves were looked at by experts, so they were actually contoured by experts before we got to use them. So for our training and validation sets, we knew where the tumors were to begin with. And the data, of course, was split 80-20 for training and validation. Okay, on to the technical stuff. Wavelets, what are they and how do they work, and how can they help us detect these small tumors? Well, for this work, we've used an ensemble of two different wavelet methods. The first is a discrete Haar wavelet, which we used on the tumors, and also a continuous wavelet process. They were also exposed to that as well. And each of these methods produced a probability, and in the end, the probabilities were multiplied together to give the probability that we actually found a tumor or not. Okay. Pre-processing steps look like this. First of all, the 3D contrast-enhanced MRI is just fed through an algorithm that just rescales everything from values of 0 to 1, and then it's deconstructed into cubes, subcubes. These subcubes at the moment are 17 by 17 by 17 voxels. Why is that a magic number? It isn't. We just found from experience that with the type of images that we were using, subcubes of this size will contain a 5 millimeter wide tumor or anything smaller. Then these are sent through a... Oh, hang on. Yeah. I just misread it there, sorry. Okay, so then what we do is we take the maximum value along the X, Y, and Z axis of these 17 by 17 subcubes, and we create a 17 by 51 2D image, and that's the thing that is actually sent to the wavelet algorithms. So a Haar wavelet, the discrete one, what does it do? Well, it consists of a discrete set of orthogonal functions, and it can be used to decompose a signal into various components. Now, when you're dealing with imaging signals, the components that the Haar wavelet will usually decompose your signal into are vertical, horizontal, and also diagonal features. So you can extract different features from the image using these wavelets. So how does that work with the tumors? Well, if you send in one of these 17 by 51 images that you've created and it actually has a tumor in it, the Haar wavelet will process that and produce the sort of result that you can see in the top figure here, in which the actual tumor or the tumor pattern appears in certain locations. And so these patterns will be repeated for any tumor that you find. And those patterns are very different, as you can see, to the one down the bottom, which is the normal tissue. So by basically covering these outputs with a binary mask and adding up the pixel values or counting the number of positive pixels under the mask versus the number of pixels that are outside the mask, you can generate a rough probability of whether or not you have a tumor. And this slide is just basically saying the same thing. This is the method we're currently using. I'm sure there's a better one. But using the current method, you simply gather up all the pixels in selective locations and compare that number to the number that is not in your selected locations, and you can generate a probability. Okay, so for the continuous wavelet function, we've used Ricker wavelets, which are normalized second derivatives of a Gaussian function. These wavelets are used in seismic research, and they're also used in imaging research. And they can separate frequency-based features, often, in some cases, better than a Fourier transform. That's what I'm trying to show here with this little demo, which I actually got from the Pi wavelets page. You can see the input function is rather complicated, and it's made up of two separate frequencies. That's the one down the bottom there. Here we go. Yes, so it's a rather complicated input function made up of two separate frequencies. When you run this through a Fourier transform, this is the output. You really can't see that there are two separate frequencies in there unless you've got a lot of experience with this. But through the wavelet transform, you can clearly see 1, 2 different frequencies in there. So we've managed to separate the frequencies quite well for this. So again, how does this work in terms of detecting tumors? Well, when you send that same 17 by 51 image through the continuous wavelet transform, you get a different output pattern for tumors than you get for normal tissue, just like we did with the Haar wavelets. And by selecting the specific features from these, you can actually train a random forest to recognize tumor versus non-tumor. So the initial size of the training set was 366 small tumors and normal tissue. We did an 80-20 split. The random forest classifier had 1,000 trees with a maximum depth of 3, and the training accuracy we ended up with was 0.89. Okay, so now we have our Haar wavelet set up generating probabilities, and we have our random forest trained to generate probabilities. So now it's time to look at some actual data, not training, not validation, but data that's actually been held back specifically for this purpose. And for our initial setup, we plucked out these 17 by 17 subcubes from different locations in the image by hand. Okay, and as I said, these images had already been contoured by experts, so we knew where the tumors were, so we could pluck out a tumor in one of the cubes and pluck out normal data in the other cubes. And the normal cubes were selected from non-diseased areas of the brain, including grey matter, white matter, and near the skull. Okay, so the initial tests were carried out on these individual subcubes, and we had a total of 19 small tumors located in 22 subjects. And during this initial testing phase, we ended up with when we measured everything, we ended up with a sensitivity of 0.74 and a specificity of 0.98 for this method. Now, you'll notice that this sensitivity is not very high. Why is that if we knew where the tumors were? Okay, so this is one of the reasons. This is an image of one of our subcubes that does in fact contain a tumor, but it also contains a small blood vessel running right alongside the small tumor. And so when we run this through our detection system, it leads to false negatives. And also, sometimes blood vessels can also lead to false positives. So you're in a healthy part of the brain, but you have a small blood vessel there, and for some reason, even this method thinks it looks like a tumor. So you can get false positives as well. But we decided to press on and run a full-scale test on real data, and that means dividing the entire 3D image up into these 17 by 17 by 17 subcubes. These subcubes overlap by necessity because if if the tumor is present, we don't want it on the side of one of the subcubes. We wanted to make sure that in at least one of them, it's somewhere near the middle. So the cubes have to overlap. This can generate about 100,000 subcubes very, very easily. And so calculation time is now a factor. Right, so we initially started out not using the Wavelet method. We started out using a different method which consisted of a liquid state machine and a random forest. And it was quite successful. It actually did predict a large number of the small tumors and gave some false positives. Unfortunately, processing the 100,000 or so or more subcubes took over 3 hours, even when running on 8 GPUs. And this is not acceptable for clinical practice. We need to be able to run these things a lot faster. This is the result of the liquid state machine, or one of the results from the liquid state machine and the random forest. As you can see, it's detecting tumors quite well. Okay, we have these probability overlays on the tumors. It's even detecting some tumors that are not in the plane of this image. Okay, so it's detecting those correctly. It also has a false positive sitting over here, but and also for the current data for the sensitivity, when we divide everything up into these subcubes, our sensitivity, instead of using the individual ones, has actually dropped to 0.23, which is not good, and we're actually trying to work on that. So compare that to the Wavelet method, which is over here. This is our initial data. You can see we are detecting this tumor, and we are detecting the two that you can't see here because they're out of plane. The false positive is gone, which is good, but one of the best or most promising things about this method is that we've actually able to cut the calculation time in half. So it was now 1.5 hours for this particular patient, which is still not great. We need to get that down, but at least it's an improvement. Okay, so doing a comparison with the current literature, which often uses various types of UNets or CNN or variations on them, we found that our sensitivity for detection is actually pretty consistent with a lot of the literature. So that's good, but it also tells us that these tumors are very, very hard to detect, and so we actually need to keep working on it. And that's what we've got here. For detecting these tumors, wavelet transforms do actually work. That's encouraging. We can also get false positives from blood vessels, which we need to deal with, and also false negatives if the blood vessel isn't a cube with a tumor. So refinement to these methods is necessary, and we're looking into various ways of doing that. I would like to thank all the people in the Chung lab for all their help with this. And that concludes my talk. Thank you very much. Yes.
Second, I'll go.
We all know
Oh, right.
very good talk. We all know, because this is mainly my research topics at Baylor. So we know for the tumor less than 2 millimeter, no matter what kind of neural network you use, it's always like a 0.2 or less than, even less than the sensitivity. Yeah. So that's very good. But we also know that for the MRI image, especially for the small tumor, the data robustness is very, very challenging. Did you ever try, even a very small data set, try using external institution data, for example, like the published data to test these things?
Okay, what do you mean, like the Bratz data set or something?
Yeah, the MRI, the T1, the different institutions, they use even slightly different in their scanning configuration. Then we use a model to train it very easily to have the robustness issue. So, for example, your model works very well in Amazon, and I change it to Baylor or Smith Clinic, then the quality going down. So have you ever tested with the other your
other data?
Yes,
we have, and the quality shoots down, as you said.
Okay.
Yes, so it does.
So still have
it's
issue.
a very difficult problem.
Very difficult.
We're trying various different ways of correcting it, like examining our current training sets with other training sets, basically generating statistics. I don't know if you're familiar with. It was called Marquee before, and now it's called BradQI.
Yeah.
It generates a whole bunch of statistics for images. We're using that to try and flush. How can we normalize these images better? We're trying to use that to actually flush out these problems right now.
Another suggestion is like now you have the computational issues because you have too many cubes. You can use we can use a high sensitive model first, but a low specificity to like countering like a 100 or 200 most highest possibility cubes. Then use your model. Then in seconds, then your models can work because you have even the lower sensitivity, but you will have a very high specificity. So combine these things together, we can remove the false positive part for the first model. Use your model as a filter. Then the combinations can solve out, can bring up a clinical solution. But it's very exciting.
Yes.
So I'm wondering about the way you're doing the classification and the sensitivity. So it's a probabilistic result that you get.
Yes.
Are you using just like, is it greater than 0.5 to call it positive?
Okay, for actually detecting a tumor?
Yeah.
Yes. Okay. For these particular ones, saying we have something or we don't, I believe it was actually 0.6.
Okay, so if you lowered that, then you would increase the
0.6,
sensitivity and decrease the
like you saw on the
right?
images there, where we had the probability distribution over the first image, because we haven't created it over the second one yet, but for the first one from the liquid state machine, you can actually see a probability distribution that was generated over there. And so the threshold was greater than 0.6.
So how do you choose that threshold?
The threshold at the moment was chosen in a rather ad hoc way. because if you take anything greater than 0, the whole image will just light up with stuff. So we had to get something reasonable, and by basically trial and error, we found that 0.6 for these images, coming back to your point about the different data sets. So for these images, that's what seemed to work best for us, but for that particular image set.
Thank you, Dr. Elliott.